All right, gang, here we go. This is Chem 2, Unit 6. We're talking about enthalpy today. All right, so last video we talked all about thermodynamic values, thermodynamic quantities. We talked about internal energy, we talked about heat, we talked about work. Remember, we had this idea of the system versus the surroundings, and we talked about how things can come in or leave the system. Remember, and so whenever we do anything to do with thermodynamics, we're really talking about what's going on in our system versus our surroundings. And remember, we talked about how internal energy and a lot of these thermodynamic values are really hard to measure, or they're also very just not useful knowing the exact magnitude of these quantities. So really, when we talk about thermodynamics, we're talking about what's crossing the boundary, right? We're talking about what's the change in. Are we losing heat? Are we doing work on the surroundings? Are we gaining heat? Is work being done on the system, kind of thing? All right, so this brings us to this new idea about called enthalpy. Okay, and so enthalpy is a really useful term in chemistry because of the idea that when we do chemical processes, for the most part, we can assume that we're staying at a constant pressure, because most of the time in chemistry, when we do a reaction, we just do it in the laboratory, which is atmospheric pressure, and over the course of the experiment, the atmospheric pressure is not going to change. Okay, and so we can assume that we're at a constant pressure, and this allows this idea of enthalpy to be very, very useful to chemists. Outside of the chemistry world, enthalpy gets less and less useful, but for chemists specifically, enthalpy is actually quite useful. So it's probably the go-to thermodynamic quantity most chemistry textbooks use, and there's lots of tabulated information about it, and we'll talk about that more as we move through the content. All right. So anyway. So enthalpy is defined as the internal energy plus the pressure times the volume. Okay, enthalpy. Enthalpy, we use a capital H for enthalpy because enthalpy starts with an H. Yeah, I'm just teasing. I have no idea why we choose capital H for enthalpy. But anyway, so we can't use E because that was internal energy. But and yeah. So anyway, H equals E plus PV. Now remember, we just talked about how we have the system and the surroundings. Okay, we don't really care about what the exact quantity is of those thermodynamic values. We really just care about what the change is, what's crossing that boundary, what's coming in, what's going out. And so we'll add this change in value here because that's really what we care about knowing. So if we add the change here, we got to add it to this side. Okay, delta, the change in internal energy plus, pressure times volume. But remember, because we're doing it in the atmosphere, we're at constant pressure, so the change in pressure is just equal to whatever the pressure is, so we can get rid of this change in value. And so really, the enthalpy is equal to the change in internal energy times the pressure times the change in volume. All right. Now, the cool part is that because, remember, this is from the first law of thermodynamics, right? Our change in internal energy is equal to Q plus W, and work is equal to the negative pressure times change in volume, right? Remember this, work equals negative P delta V. Okay, so we can plug these ideas in. So our delta E is equal to Q plus W, and our P delta V is equal to negative W, right? We're plugging in these guys here. And so really this W will cancel here, and we end up with delta H is equal to Q. So essentially, this means that if we can calculate the change in enthalpy, we know the heat that was gained or lost. Super helpful. All right. So again, because Q and delta H are exactly related to each other, we can talk about endothermic and exothermic processes exactly the same. Remember, if anything is gained by our system, it's always a positive thermodynamic value, and if anything is lost by our system, it's always a negative thermodynamic value. All right. So if heat is gained by our system, that means we have a positive delta H. All right, our change in enthalpy is positive. If heat is lost by our system, that means we have a negative enthalpy. All right, heat is lost. And so we've got endothermic reactions are heat gained, exothermics are heat lost. Super easy. Okay, you're like, wow, is this all there is? Just about. Okay, so a chemical reaction that gives off heat to its surroundings is said to be exothermic. Very good. All right, exothermic, and has a negative value of delta H. Okay. Oh, So it'd be D. Very good. Nice. All right. Practice exercise 2 says molten gold poured into a mold solidifies at atmospheric pressure. With the gold defined as the system is the solidification an exothermic or endothermic process. So you're starting at a liquid state, right, which is we'd say the liquid might be at that energy state. And then when we solidify, we go down here, and that's at a lower energy state than the liquid. And so we lose this energy, right? So that means it's an exothermic process, right? Exothermic process. Cool. All right. Change in enthalpy. Okay. We can calculate change in enthalpy by just taking the enthalpy of all the products minus the enthalpy of all the reactants. Okay, products minus reactants. And you'll see this pop up all the time in thermodynamics, this products minus reactants. Some of the products minus some of the reactants. All the time. When we did bond enthalpy a couple units ago now, essentially we just did products minus reactants. Okay, same idea here. So in this specific reaction here, we're burning methane, right? This is a combustion reaction, CH4 plus 2O2, excuse me, goes to CO2 plus 2H2O. Okay, so we're going from methane to carbon dioxide and water, just simple combustion reaction. And you know, because it's combustion, it's an exothermic reaction, and so that's signified with us going from our reactants up here to our products. And so when that occurs, we lose negative 890 kilojoules of energy from our system, or it's exothermic reaction, 890 kilojoules. All right, and then if we reversed our reaction, notice that it has the same thermodynamic values because those quantities, those magnitudes of enthalpy are the same, right? Reactants up here, products down here. And you can see how these guys are exactly the same, but it's backwards now. So now we have a positive 890. So the reverse reaction has the equal absolute value of the change of enthalpy is equal to one another. You just have to change the sign, okay? So this value, or this quantity that we just saw here, this 890, has a special name. This is called the delta H of reaction, or the enthalpy of reaction, and sometimes you might hear it called the heat of reaction. This is kind of an older term that's kind of falling out of favor from what I've seen. Okay, enthalpy of reaction is a little bit more common, but anyway, so delta H of reaction as well. All right, so here we've got hydrogen, okay, burning it in the presence of oxygen. Okay, and then we form water, and no exothermic reaction, so our delta H will be negative. Pretty easy, okay. Now a couple of things here that we have to keep track of. All right, enthalpy is an extensive property. Remember, extensive means it depends on the amount. Okay, on amount. Okay, so remember, density, if you have a chunk of gold that's about the size of a nickel versus a chunk of gold that's the size of a cow, okay, I don't know why I said cow, but I did. All right, the density of that gold will be exactly the same, right? Because it doesn't matter how much you have, it's that ratio of mass to volume, okay? Now, but if you have the mass of the gold of that nickel, that gold-sized nickel would be, very small, especially compared to the mass of a gold-sized cow. Okay, and so the mass is an extensive property because it matters how much you have. Enthalpy is the same idea. If you have more hydrogen that you're burning, you're going to get more kilojoules produced. So essentially, when we talk about enthalpy, really we're talking about it's a kilojoules per mole. Okay. All right, so it's a per mole of our reaction. So the amount of kilojoules we get goes up as the number of moles we're reacting goes up or goes down, as we reduce that, or depending on if it's endothermic or exothermic, you just follow the signs. Okay, if we reverse our reaction, if we do the reverse reaction, all we have to do is switch the signs. That's not what number says. The enthalpy change for reaction is equal in magnitude but opposite in sign to delta H for the reverse reaction. And then finally, number 3, the enthalpy change for a reaction depends on the states of the reactants in the products. Okay, so this is kind of an interesting idea. Over here, we reacted hydrogen gas and oxygen gas. Well, hydrogen gases here are going to be at a relatively high energy state. So if for some reason you manage to burn a liquid hydrogen, liquid oxygen, you would get a different enthalpy change, okay, because the liquid states of those are at a different level of energy. Okay, so here we've got our gases here. So the liquid states of hydrogen and oxygen would be at a different energy level, so we'd get a different delta H. So when you're talking about enthalpy changes, you have to pay attention to what your states of matter are. And depending on what your states of matter are, you're going to have different values that kind of kick out at you. All right. The other thing I want you to pay attention to is because enthalpy of reaction, so we'll make a little note here, delta H of reaction is given, the units for this is always in kilojoules, okay? That's how it's given to you, but really I want you to think about it as kilojoules per mole. Okay, so you have to think about, and this is per mole of reaction. Okay, so you have to use your stoichiometric coefficients in order to keep track of what's going on here. All right, so let's do a couple practice problems. All right. Oop, too far. Okay, so practice exercise 1, we'll do both of them. All right, the complete combustion of ethanol, C2H5 molar mass, that's nice of them, proceeds as follows. So here's the reaction. We've got liquid methanol with 3 oxygens yields carbon dioxide and water, and this is the delta H of reaction. It says what is the enthalpy change for the combustion of 15 grams of ethanol. All right, so we need to figure out the enthalpy change. Well, this is pretty easy. So we're starting with what we know. Okay, this is going to be very similar to what we did with stoichiometry in Unit 3. So we got 15 grams of ethanol, so ethanol I'm going to abbreviate as ETOH because ethanol, ET, and then the all part, remember all means it's an alcohol, okay, and that's the OH part that's on there. All right, so we're going to convert this. Remember, I just told you to think about enthalpy as in terms of kilojoules per mole. Okay, so we're going to stick that mole down there. All right, so that means we have to turn our ethanol into moles. So we'll put grams up here, moles down here. All right, 1 mole, and they already give us the molar mass. That's really nice. So we have 46.0 grams per mole. Now we're in moles of ethanol, okay? And we need to cancel out our moles of ethanol and get to kilojoules, okay? Oh, you guys should have stopped me. I totally screwed this up. Whoops. Eraser. I'm sure a bunch of you guys are screaming at your screen right now like, what is he doing? All right, anyway. So we're going to put grams in the bottom, moles in the top. There we go. And then 1 mole and 46.0 grams. There we go. All right. So now we need our moles to cancel, right? And we're going to kilojoules, which is the whole idea. And this is in kilojoules per mole. Now this mole, you have to think about what you're starting with, and you have to look at their coefficient. Now there's 1 ethanol, so that makes our life easier. So we'll put a 1 there, and then we'll put the negative 555 up here. All right. So we'll take 15 divided by 46 times negative 555, and we get negative 180.97. Okay, and we need 3 sig figs because this has 15 grams. We got the 3 sig figs right there. So so 181, negative 181 kilojoules. All right, so there's our answer right there. All right, let's do one more. Okay, hydrogen peroxide can decompose to water and oxygen by the following reaction. Calculate the quantity of heat released when 5 grams of hydrogen peroxide decomposes at constant pressure. All right, so we've got 5.00 grams of H2O2. Okay, and we are converting this into the quantity of heat released, or just the enthalpy change. All right, so same idea. Okay, so put grams of H2O2 in the bottom. Okay, moles in the top, so we got 1. All right, so that means we need figure out the molar mass. So 2 hydrogens, 2 oxygens, add those guys up. Well, so we have 2 times 1.01 and 2 times 16.00. All right, so we get 32 plus 2.20, so it would be 34.02 grams per mole. So we'll put that in at 34.02 grams per mole. All right, is that right? Am I doing this right? I'm going to put a line there. 32 plus 2. All right, cool. 5 divided by 34, and now we're in moles. So now we're going to use our enthalpy change right here. Remember, this is in kilojoules per mole of the reaction. Okay, so we're going to put moles of our hydrogen peroxide in the bottom and then kilojoules in the top. Now the number for the kilojoules is just going to stay the same, negative 196. But because we're reacting hydrogen peroxide, okay, we use hydrogen peroxide's coefficient, which is that 2. So we'll throw that 2 in there. All right. So now we'll take our 5 divided by our 34.02, multiply it by negative 196, and then divide by 2. Okay, and we get negative 14, and we want 3 sig figs, so 14.4 kilojoules. So this reaction is exothermic. Pretty awesome, yeah? Okay, so anyway, so that's about it for enthalpy changes. The textbook problems has a lot of different ways to look at it, but essentially you're just messing with these units. You've got this new tool in your belt to help you keep track of your thermodynamic quantities, your thermochemical, your enthalpy, and all that stuff. Anyway, so do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.